Okay, so last time we sort of recapped subspaces, and we got this idea. We've got these vectors in n-dimensional space, and we can add them, we can multiply them, we can do various things. And we've got a subspace, so if we take any two and we take a linear combination of them, we stay in the same set. That's all good. So we can use that for linear models now. So let's start with the most sort of abstract form of the linear model that says our n-dimensional vector, which is our observations, can be written as some vector of, we're going to call it mean, expected, we just call it eta, plus some sort of noise. And the only thing we're going to assume on the noise is that basically the expected value is 0 and the variance is sigma squared I, so they're independent, etc. At this point, we're not doing anything more than that. And we're going to say, let's assume that this vector here, so basically you said our y equals some vector plus some noise vector. This vector eta is going to be in some subspace. And if that subspace is Rn, we will call it a linear model. So we haven't really added much to it yet. And the idea is that basically when we talk about a linear model, we're just saying our vector lies in some subspace. That's all we're doing. We've got away from that idea. If you think about it before, we had that our eta equals x beta. And so I said that, that's how we defined our model, y equals x beta plus noise. But now we're basically saying, no, we've just got to the point that eta just lies in some subspace. And that's it. So you've got Rn, inside that you've got a subspace. And as long as our eta lies in that, we say we've got a linear model. That's it. What does that subspace look like? Well, if you think about it, if we did eta equals x beta, basically it's going to be such that because they're linearly independent, the columns of x, because that beta is just a load of coefficients, our columns of x form the basis for m. So when we say that y equals x beta, we're saying that our eta lies in the subspace, the basis of which is the columns of m. That's it. And the nice thing is even though we might change our parameterization to some extent, because the way we change our parameterization, they are equivalent. Even though there's two ways of describing it with two different bases, the bases are for the same subspace. So they are equivalent when we look at reparameterization of factors. So the next thing we're going to do is we're going to introduce or remind ourselves of a projection matrix. Remember when we wanted to get the least squares, we had x transpose x to minus 1, x transpose y. But if we pre-multiply that, this thing here, we're going to call P. And it's called a projection matrix. So we take our matrix X and we form this thing and we're going to call it P. And I'll explain in a while why we call it a projection matrix. But basically, P is just going to be what we call a projection matrix in that form, or generally a projection operator. And the whole idea is that somehow we're going to create this thing that's going to take a vector and return another vector. So it's going to be, and we're going to call it P. And the way it acts on it is it's going to project them down into the same subspace. So before we're going to do that, we're just going to talk about a thing called the orthogonal complement. So we've got Rn, and then we've got this subspace within it, M. And we're going to have a thing called M perp. So that's what this is, M perp. And basically, you're looking and you're finding every single vector that's in Rn that basically is orthogonal to every vector in M. So it's almost like you've done a classification. You've taken Rn and you go and grab a vector. And with that vector, it can either be in M, which we'll call it an X, or it's not in M. In fact, it's at right angles to M. So we split the whole world to every vector is either in this subspace or not in this subspace. And by not in this subspace, we mean it's orthogonal to some vector in this subspace. So you sort of got to think about this sort of like big set, and you split it into a load of vectors we care about, and a load of vectors that basically are orthogonal or right angles to the ones that we care about. And we're going to call that our orthogonal complement. So first of all, we should know that if M is a vector subspace of dimension P, so remember that's the number of bases we need to make it, and that's always the same. You can't change the basis and you get more or less. So it's dimension P. Then M perp is a vector space of dimension n minus P. So you've taken your n-dimensional space and you split it into one subspace of dimension P, and the other subspace is n minus P. So let's think about one we looked at before. We had this M1, and we defined this. This was all the vectors of the form x1, x2, 0. So M1 perp is going to be all the v's in R3, such that v times x equals 0 for all x. Well, if you think about it, we need this times some vector equal to 0. So if I denote my v as v1, v2, v3, basically you say that for this to be equal to 0, x1 v1 plus x2 v2 equals 0 for all x1, x2. Which implies, if you quickly solve it, that v1 equals v2, which equals 0. So our M-perp is all vectors of the form 0, 0, v3, where v3 is just a real number. Which, if you think about it, is the span of the vector 0, 0, 1. So that's it. It's a one-dimensional. This one up here was two-dimensional. This is one-dimensional. They add together to give us three-dimensional space. Next, we're going to think about it. We're going to say you've got Rm, which is a vector subspace. There's always vectors. We can take any arbitrary vector in n-dimensional space, which we call y, and you can show that that can be expressed as the sum of a vector in the subspace and a vector in M-perp. So what we're saying is you take any vector in this subspace, in this Rn, and it can be written as a sum of two vectors, one that comes from our subspace, one that comes from the orthogonal subspace. That's it. I'm not going to go through the proof in these lectures. The proof's in the handout if you want to go and look at it. But it's really, really cool because it basically means we can take any vector and we can split it into two parts. Two parts are orthogonal to one. One in my subspace, one in the rest. Now we get back to the idea of projection. We're going to say an orthogonal projection on the subspace M is going to be some operator that will take any vector in Rn and basically spit out the bit of the vector that lies in our subspace. So we've got this P, it takes a vector and it does the job for us. It sort of breaks into two bits and it goes, this bit is in your subspace, this is in your M-perp, your other subspace. And obviously if I wanted to project into M-perp instead of into M, you would just use I minus P. So it's almost like the opposite. Now that would project into M-perp and the stuff that would left over would be the stuff in the subspace. So let's think about our example. We've got our M1 in R3, which was x1, x2, 0. We've got some arbitrary vector, y1, y2, y3 in three-dimensional space. And what I'd like to do is take this and split it so I get my vector in that x1, x2, 0 space and the vector in the 0, 0, v3 space. So that's what we want. We want to be able to split it into this form plus this form. And the orthogonal projection would take any vector and spit out y1, y2, 0. And you could think about writing your projection matrix to do that. And it would be a nice matrix in this form that would spit it out. Why do we care? Okay. The nice thing about our orthogonal projection M is if I take any arbitrary vector in Rn and then I have some arbitrary vector in my subspace, then the sum of the squares, which we do y minus mu norm squared, will always be greater than or equal to y minus our projection matrix squared. So the idea is you could find other ways of choosing a vector in that, but if you wanted to get the smallest distance in terms of our norm between our observed vector, in this case y, and the vector that's been in this subspace, so the best one in the subspace, the one that's closest to it, you're not going to do better than your projection matrix. Again, there's a proof of this, it's in the notes, I'm not going to go through it here. What does that mean? Basically, your projection is going to give you your least squares estimates. The whole idea is you've got this projection vector and you're splitting it. What you're doing is you're taking your data and you're splitting it into two parts. One in the subspace, which is the subspace you care about, one at right angles to that, and you're not going to do better than using a projection matrix. Okay, so now we need to find this orthogonal projection matrix. So just to recap what we're doing, we've got a linear mapping P, and it's an orthogonal projection on M if and only if, first of all, that when we take P of y, we get a vector in M. When we get y minus P of y, we get a vector in M-perp for all our y. And these two conditions, such that when we do it, when we apply this projection matrix on a vector, it spits out a vector in the subspace. And when we do y minus the projection, we get something in the orthogonal subspace. Those two constraints we're going to call the normal equations. So how are we going to find it? How are we going to do this? Well, the nice thing is, if you have any arbitrary n by n matrix P, the mapping of Py is the orthogonal projection on the range of P if and only if P equals P squared equals P2. Okay? So as long as you've got this thing which we call idemnipotence, that is, your mapping has these properties that when you multiply it by itself, you still get P. If you take the transpose of it, you still get P. That is your orthogonal projection. So let's show that this is what we had all along. So let's go right back to start. We've got y equals eta plus e. We've got a constraint on e, etc. And we've got a linear model, eta equals x beta. So this is the thing we want to sort of project onto, where x is n by n. We know that P, which is x transpose x to the minus 1, x transpose, is symmetric and idemnipotent. That's good. Also, we know that the range of P, so things this projects, is the column space of x, or basically, it's the linear subspace. So we have a P that is symmetric, idemnipotent, and the range is the subspace that we want. Hence, this thing here is the orthogonal projection of M. That little function there, x transpose x to the minus 1, x transpose, when applied to any y, we'll project it down into our subspace defined by x beta. We did it with calculus, we've done it with linear algebra, but we're now seeing that this abstract subspace version, it still works. How could we use this even further? Well, now we've got this Rn and we had a subspace. We can now say, well, let's consider an even smaller subspace, which we'll call H. So I've got subspace H that lies beside M, which lies beside Rn. And we're going to say that P0 is the dimension of H, which is smaller than P, which is the dimension of M, which is smaller than N. So we've got our general linear model, eta is in M, and then we've got a new hypothesis that says, well, actually, eta is in this smaller subspace. So you could do the difference between having a full model in linear regression and just having the null model, the intercept. That's a smaller subspace. And what we can do is we can create an analysis of variance table, all in terms of norm squared. So here is the difference between the sum of the squares between our two models, our big model and our smaller model. Here is the residuals of what happens when we take our big model and see what's left over. We get our total sum of squares, which is basically our data minus the smallest model we've got. You should find that this sum of squares plus this sum of squares equals this sum of squares. This degrees of freedom plus this degrees of freedom gives this degrees of freedom. If I take my sum of squares and I divide it by the degrees of freedom, we get a thing called the mean sum of squares, and this is under the null space. This is under the full space, and here's our F ratio. And basically our P is an orthogonal projection onto M, and our P0 is the equivalent orthogonal projection onto our null, or smaller model, H. And the whole idea is you can actually now just do the expected value. I'm just going to quickly step through these, but I can say, well, what's the expected value of our observed minus our fitted squared? Well, you can rewrite this as I minus P, so that's good. It's the expected value of that. And we've showed ages back, you can write this as M minus P sigma squared. So that the expected value of the MSE is sigma squared. So we know this number here, its expected value is sigma squared. What about the top line? So if we go back to this top line here, we're going to look at these sum of squares and say, well, what's the expected value of that? Because then I can get the expected value of this bit here. Well, we can do some rearrangement. We can go P minus P, this is our sum of squares. We can split it. We can basically add in this extra term because this is just a constant, it makes no difference. Then we can split it and expand it, and we've got all these terms. We know that P minus P is an orthogonal projection on a new vector subspace, which is the intercept of M and H. So we've got this complicated, basically it's a Russian doll of subspaces now. But the good thing is, because it's just a projection, we can just think it in terms of linear squares and say the expected value of this is going to be P minus P0 sigma squared. We know that eta is just some constant in all this when it comes to expected value. This is the only thing that's random. So this, we can write this term as basically, it's just a constant. This is saying what's the expected value of a constant. There's no y in there. It's just this constant. The expected value of our eta, so this is our cross product terms. Basically, you can bring these two out. You get expected value of y minus eta. Our whole idea is this is how we've defined our model, so that's 0. So when you put all that together, you basically finally get that the expected value of the top line is sigma squared plus this term here. Okay, so it's the same in the second line, but some extra bit, some non-negative extra bit. What is that extra bit? Well, if eta is in our null space, if our null hypothesis is true, then that means that this is equal to 0. Fine. So that whole second term disappears. But if not, the extra bit is how much we're departing away from that. So our extra value in that top line is sigma squared if h0 is true, or sigma squared plus some non-negative bit. So let's go back and think about what we just said there. We did a lot of jiggery-pokery, but all we're saying is this number is sigma squared plus an extra bit, and the extra bit basically gets larger and larger if my null's not true. If my null is true, it's just sigma squared, while this bit is sigma squared. So what's this? If the null is true, it's sigma squared over sigma squared is approximately 1. If the null is not true, it's sigma squared plus a positive number over sigma squared. So basically f is either going to be 1 if the null is true, or get larger and larger and larger as you deviate away. So that's it. That is your f statistic in this complicated space of Russian doll, of subspaces, etc. So I just wanted to show that underneath least squares there is, I don't know if it's underneath or a higher level, you can think of it either way, but basically there's a more complicated form. You could do the whole thing in subspaces. You know, when you in first year we wrote it as a linear equation, then we got to second year and it was a matrix equation where we sit, and now you're saying, well, matrices are just an object in a subspace and it's all done in subspaces. It doesn't change anything. You're still going to use matrices in art, that's it. But if you want to do something much more complicated with this, you can do it in this major subspace. And it also shows that even though we had two different parameterization for factors in the different matrices, to some extent, they were doing exactly the same thing. They were just projections on a subspace. Now we've got that, we're just going to, next time, have a look at how we can apply this to generalized least squares. See you next time.